Thank you. I will continue. Sorry if you missed all that. So, we have the enormous above ground stores of soil carbon here in the topsoil systems, but below ground also is enormous. So just to put that in context of all the other biomes, we're dealing with high carbon systems here, and they have implications for climate change. But we're dealing with some challenges here in Hawaiʻi, across the islands and the different ecosystems that we have, and some of that has to do with the high variability of soils in both space and time, and of course those are impacted by things like climate and our very steep climate gradients that we have across the islands, as well as the complexity of other drivers, thinking about the mineralogy, the age of the volcanics underlying those soils. So we're dealing with a great deal of complexity and kind of the drivers of soil carbon. And for that reason and others, the widely used models like Century and Dacent don't work well for capturing soil carbon in these systems. They actually max out before reaching the high carbon that we see in these soils here. So we're trying to come up with some better methods to quantify that soil carbon. And here's just another example of the soil or the island ages that we have, going from the still forming volcanics on Big Island all the way up to 0.7 million year old. And that manifests in our soil diversity that we see across the island. So this is mapped from the NRCS, and these are soil suborders across the islands. You can see the enormous diversity that we have here, and those reflect different processes happening in terms of above ground carbon, below ground carbon, climate factors, mineralogy, all of that. Okay, so what do we have available in terms of soil carbon maps to work with right now? Well, one is soil grids, and it's 250-meter resolution. But the problem with that is it's 0 to 30 centimeter carbon stocks. And as you may know, we have extremely deep soils here, and 30 centimeters does not capture the full profiles that we have across the island. In some cases it does, but it's not sufficient for our purposes. Although it does come with uncertainty. You can see that there is extremely high uncertainty in a lot of areas across the islands, especially those more mountainous areas and areas with high above ground biomass, which sometimes reflect high below ground carbon as well. So another data source is Open Land Map, and the issue with this is that they only have percent carbon, not stock data. So this is for 0 to 10 centimeter depth. They have a bunch of different depth increments all the way down to 200 plus centimeters. But again, that is not a stock, that is just a percent carbon. So it's not good enough for our purposes here. And there's pretty high uncertainty associated with that as well. And the final data source we have available as far as mapped carbon comes from the carbon assessment of Hawaiʻi, and that is based on Surgo data. This is NRCS from the USDA, and that's basically mapped to the soil, the mapping units that they use. And so you can see kind of the wide areas, basically taking organic carbon estimates, multiplying it by 58%, and saying that that's the soil carbon in this whole area. And of course, that's not good enough for our purposes. We know that soil carbon varies a lot more than that. So that's a little bit of the reasoning for doing this work. What we have to work with here, and what I've been working with, is a couple of different data sets. So one is imputed soil carbon stock, or soil carbon percentage, excuse me, from 0 to 20 centimeter depth. And those data come from the Hawaiʻi Soil Carbon Database, forest inventory and analysis data. So that's FIA data from the Forest Service, and then the Hawaiʻi Soil Health Database. And what we end up with those data is 850 unique locations across the islands. With the second data set, I've imputed stocks to 1 meter from just the soil carbon database and the FIA data. And we end up with 916 unique locations across the islands. And just to show when you map that out, you get this distribution of soil carbon for the first data set, and we have kind of lower carbon estimates in the kind of whiter color, and then the darker red are higher carbon estimates. But these are mainly to show just the distribution of data. You can see we have some data poor areas. And then when we have the depths as well, we're very data poor in, Leeward, Big Island, Hawaiʻi. But those are those are the soil carbon data going into these machine learning models. So before I get into that, I just want to say a little bit about process-based modeling, because that's the kind of the traditional method, and it's a starting point. And that's where we're basically attempting to simulate the underlying decomposition processes that are happening, carbon transformations. A lot of those are microbially influenced, and you can have different pooled models. So anything from 1 pool models to 5+ pools, depending on how fast you think the decomposition is happening. And I have an example here of Dr. Kathy Todd Brown's model, where we have the rate of change in soil carbon stocks equaling the net primary production minus the decomposition rate, temperature sensitivity, moisture sensitivity, and current soil carbon stock. And that's a fairly simplistic model. But you can imagine that when you have localized parameters for for each of those, you're going to get some pretty site-specific estimates for soil carbon, and those aren't necessarily going to be able to be extrapolated for wall-to-wall mapping like we're trying to do here. They're also, means focused. And so what we're trying to do is this generative method instead. And this is more data-driven. You do need a great deal of data to go into these models, but they're a lot better at finding connections in complex systems. And basically, you can generate distributions of data instead of means. So when we look at soil carbon data across an area, you can imagine kind of a homogeneous field, and you might get fairly similar soil carbon data when you go soil sample in a couple of point locations. But then think about the complex topography we have here. We have land uses and above ground carbon. So a mean is not necessarily representative of that system. And so with this method, or these methods that I'll be talking about, they really can capture those distributions, different types of distributions, instead of just baking everything down into a mean. They can also deal with time series data and data at multiple spatial scales. So I'll be talking about, I'll be sharing results from 3 machine learning approaches. I won't go too much into the actual approaches, but one of them is the random forest method. And so what I've done with that method is to, for each soil carbon point estimate, or observation, rather, we have a set of covariates, and that would be things like climate data, topography data, set a radius around that point, then shuffle that carbon location to basically bolster your data set, get a lot more data, because that 900 observations is not enough really to do this type of work. So we come up with kind of a simulated data set in that way, and train random forest and make predictions. And a benefit of doing that is that you can actually get a variable importance coming out of your random forest model, and make some interpretations from that. So the second method is convolutional neural networks. And so with that method, we've actually trained one neural network to generate soil carbon distributions by grouping soil estimates into 10 different quantiles. And then we train a second completely separate neural network on those generated distributions. So that second neural network, it never sees the truth data. And it's what's used to make the new soil carbon predictions. And neural networks are really good for thinking about spatial data and finding spatial patterns. They're originally used for looking at patterns in images and connections in images. So that's why we would think this method would work well for soil carbon with our spatial patterns. And then the third method is transformers. So that's a newer method that we're developing and basically training data on sequences to generate kind of the next value in the sequence. And this, what transformers are good for is really taking advantage of time series data and a lot of things that we know vary with and influence soil carbon are time series data, climate data, Landsat, spectral values, all that. So we can pair those data with a soil carbon estimate for an observation for a location and kind of predict the next sequence. So that's the transformers model. And I will jump straight into some of the results from the different methods. Sorry, this is hard to see, but this is from the random forest method. So what I was trying to do with this was look at different areas of the island and different kind of driver groupings. So I grouped the variables into biological, physical, and climate drivers. And that's what I was looking at in the variable importance. So we have our carbon predictions, carbon stocks here, and I just put two examples from what we saw in terms of, these are lower carbon predicted areas from that random forest method, and the driver variables we saw on the lower end, that was just a climate driver. Medium, but still very low carbon predictions. Those were predicted by biological and climate, half and half. And then as we go a little bit higher in soil carbon, we see some of the influence from the physical topographic drivers. And then compare that to the Hilo side of the island, where we've got some higher carbon stocks and it's getting a lot more influence from the physical drivers on that side of the island. So, this is just an example to show that we can actually make some interpretations from machine learning models and get at what is driving carbon in different regions of the island. And one more example of that is just, we have the Kohala region with very high soil carbon, and so we can see in that high soil carbon region that there are some lower carbon estimates, and those lower carbon estimates are actually driven more by climate and biological, whereas the high carbon areas, again, have that physical influence, so topography potentially. So that's the random forest method. I'm going to hop straight into the convolutional neural network and show some results from that. So as I said earlier, we grouped the predictions in 10 quantiles. And so this is measured versus predicted soil carbon. And this is for each quantile. So the lower quantiles were not predicted as well using that method, but the higher ones were predicted pretty well. So to me, this shows the promise of the convolutional neural networks to actually find those patterns in the spatial data and be able to predict the higher soil carbon values that we actually have in these areas. And we can make maps from those data. So here's one example. This is from the median quantile prediction. And you can see some of the regions that are higher and lower soil carbon and think about some of the drivers in those areas. So we zoom in on kind of, that same area of Big Island I was talking about, thinking about those extreme climate gradients over here, and the high rainfall, super high biomass manifests in this soil suborder the wet insectisols, and those are high soil carbon predictions compared, say, to this insectisol, or sorry, the iridiol over here, that is the dry soil, that is, a lot lower soil carbon. And then on the slopes of Mānoa, again, those very high soil carbon areas. So just doing some visual interpretations, this seems like a promising method, and that leave one out cross-validation seemed to confirm that as well. So I do want to get into the transformers at this point. So with the transformer method, we have this set of data. So we have spectral data from Landsat. So this is blue, green, red, near infrared. We have our climate data, terrain, and then stick a soil carbon onto all of that for a location. So this is one sequence of data that goes into the transformer model. If we do that many times, this is what we come up with. Basically, we use this sequence. The next in sequence is predicted for by the transformer model. Then we rip off this soil carbon estimate before predicting the next, because we don't want to carry around our carbon with us. We want it to be making the predictions each time. And so in addition to getting a soil carbon estimate out of that transformers model, you're predicting every single one of those variables that went into that sequence. So we have, as one example, vapor pressure deficit and solar radiation. The transformer is good at getting that time component. So the cyclical components of this is vapor pressure deficit over here, other things that influence above ground and below ground carbon. Same with the actual versus predicted soil radiation on that side. So how does it do with predicting soil carbon? Well, we only have at this point 1 point in time soil carbon estimate, although we're working on bolstering our data set with multiple data points in time to see if it actually can start predicting those. But it does. You can see it's predicting cycles of carbon percent for an area. And we can debate whether or not that's something we believe, if carbon is changing in that way, but consider, what is happening, drying and wetting cycles, what happens seasonally with microbial activity, that type of thing, and perhaps soil carbon is changing throughout time for an area. And then with our cross-validation results, this is kind of what we're seeing in terms of across all the islands, 0.59 R squared. And so it seems to be, working well at predicting soil carbon here. We wanted to do a little bit more vigorous cross-validation at that point. So we did a leave one island out cross-validation. So a whole island's worth of data and then predicted on that. And this is for Oahu, and it worked very well, 0.63 R squared. So, from both of those methods, it seems that this transformer is working for predicting soil carbon. Zooming in on a test region, we just decided to look at this area that has kind of a mosaic of different land uses and think about what might be happening over time, both above ground and below ground in terms of carbon cycling. And I have a video, I don't know if you'll see if we can get it to play here. Very so.
I think if you just move the window to the screen one should work.
Then do I have to switch?
Yeah, it works. Yes, it's appearing on the Zoom thing.
Okay, so what we're getting here is actual soil carbon predictions in time. I know you can't see it that well, but it's lower to higher soil carbon from purple to yellow. Yeah, so this is across years. So this is just to show kind of the promise of this method. You can actually look at patterns potentially in soil carbon over time and look at these lower carbon areas kind of here and here, with different land use, higher carbon areas with the higher above ground carbon. So from that, let's see. So, this is just for 2024. So from that, yeah, we can start seeing there are actual, spatial patterns, there are patterns in space, there are patterns in time, and this is what we expect out of soil carbon estimates. This is a very new method in development, so this is where we're at with it at this point, just kind of looking at testing some different regions. And trying to pick out what's happening over time with soil carbon. But they seem to be reasonable patterns that are really following some things we know about drying flooding cycles over time. And I think, yeah, this is basically the same, showing the same pattern, but just the mean soil carbon for a particular location across years. So showing some promise in time series prediction. And yeah, with that, just leave you with a few takeaways of this work so far. We have some deep learning approaches that are effectively predicting and generating soil carbon distributions in space and time. We can actually do interpretation of the supposed black box methods that we're using. It is possible, just have to be creative about the questions you ask and the way that you ask them. And, compared to some of those process-based models that were used in the past, we can actually get better carbon predictions in these high carbon areas with these deep learning methods compared to those models. So that's all I have for you, and I'm happy to take any questions. Thank you.
Well, we'd like to open the floor to a Q&A as well to anybody on Zoom that have questions. I was wondering